this out of the box, but the community works around our models, and we learn from the community how our models can be customized or deployed in new settings. So how are these open source models trained? So I'll give you a very high level overview of the different stages of LLM training. And typically LLMs are trained in 3 stages: pre-training, instruction tuning, and learning from human feedback. So the idea behind pre-training is very simple. You take a piece of text and you pass word by word or token by token through the large language model and ask the model to predict the next token. So the idea itself is very simple. The task is the next token prediction. Each token is roughly 0.75 word. The vocabulary size is roughly tens of thousands of tokens, or sometimes hundreds of thousands. And each token is basically represented as an integer, and it has an embedding associated with it. And so the task of the model is to take in a sequence of embeddings or tokens and predict the next token. Although the concept is very simple, in practice it's actually very hard. Why is it hard? Because it requires a lot of effort in building the data sets. The data sets are huge. They are order of trillions of tokens, or tens of trillions of tokens. It requires pre-processing, cleaning, deduplication, curation. And there's again a common belief that more data leads to better performance, but that's not necessarily the case. If you have noise in your data, that can actually hurt the model performance. It also requires a lot of investment. These models are huge. It can go up to hundreds of billions or even trillions of parameters. Each model takes tens to hundreds of millions of dollars to train. And the hardest part is you don't get multiple chances to train the model. Because it's so expensive, if something goes wrong in your training, it's very difficult to get the investment to do another training run, because typically for small companies, you don't get that kind of budget. If you do a model run and it's not successful, it becomes harder to get the funding for the next run. And this is hard because the best hyperparameters for a smaller model might not be the best for a larger model. Here I'm showing you some hyperparameters for Llama 1 model family sizes. And you might ask, why are the number of layers 80 and not 82 in Llama 65B? And the answer is we don't know. There's a lot of things that have been decided by intuition, and it's not exact science. So you need a lot of experience and intuition working with these models to come up with things that are very likely to work, but we're still not very mature with the science of what is the best way to train the model, or what's the best architecture, what's the best data set mixture. So can we use this pre-trained model? So let's say if you want to use this pre-trained model and ask it to write a Python function to find whether the input number is prime or not. And the model might give you a response like this. It continues the text, gives an example, and describes the approach, but it might not give you the code. And this is because the model is trained to do this. It's trained to predict the next token. So it predicts the most likely token from the text data it's been trained on. But there is a way to trick the model. If you give this input, like as a Python function definition and a docstring to get the same function, the model actually produces the code. And so this shows you that model actually knows the answer, but it is not aligned with human preferences. It's not trained to interact with humans in the way humans want to. And this is why we need the next 2 stages. So in the instruction tuning stage, instead of just a string of text, we have prompt response pairs. So here we are giving the prompt, but in the way humans want to interact with the model. So for example, this prompt to write a Python function, and the response is directly the code because that's what humans want as the response. And the technique is very simple. Again, we are doing next token prediction, but the only difference is we are going to mask the prompt itself. We are going to do prediction only for the response. So the data set is paired prompt response pairs. We typically use hundreds of thousands of instructions. The task is next word prediction, but just we mask the input instruction. It requires way less compute, order of 100 GPUs for a few hours or days is typically sufficient to do instruction fine-tuning. And then the last steps is learning from human feedback, and here the idea is that human preferences are cheaper or easier to obtain than full human annotation. If I give you a prompt like this and 2 responses, it's much easier for a human to decide which response is better than to write the whole response from scratch. And so this allows us to scale data faster. And there are 2 main techniques, reinforcement learning from human feedback and direct preference optimization, where we use this kind of preference data to fine-tune the model further. So just to summarize, these are the 3 stages. They have different orders of data set and compute requirement, and the task is slightly different. And all the open source models we have I've been trained using these techniques. And so I won't go into the details of the model architecture itself, but I'll show you this nice graph of performance to cost ratio, which kind of shows that we really try to optimize this metric. We try to get the best performance out of our models of a particular size. So here on the x-axis we have the active parameters, which is directly proportional to the cost of running through the model. And on the y-axis we have a popular benchmark, MMLU. So we try to be in the top left corner to get more performance with a lower cost. We recently released the CodeStral model, CodeStral 22B. It's a dense transformer model trained specifically for code. And again, we are trying to optimize performance and speed. It's fluent in 80+ programming languages, and it has both instruct and fill in the middle mode, which means that you can use it for code completion in your code editor, just like GitHub Copilot, but also you can use it to ask questions about the bugs or errors you're facing, just like you would put it in ChatGPT. So it outperforms CodeLlama 70B, DeepSeek Coder 33B, Llama 370B, while being a significantly smaller model. So again, we are getting more performance out of a model of a particular size. And it also has a longer context window than the other open source code models. It is multilingual. We trained it with more than 80 programming languages, and across all these different languages, it tends to perform better than the other models. So it's free to use on our chat interface, chat.mistral.ai. We also have the API access available on Lab Platform, which is our platform API endpoint, and here it's also free to use till I believe end of July. We also have integration with VS Code and JetBrains, so you can download a plugin in VS Code or JetBrains and use it as a coding assistant for code completion. So in the end, I would just discuss some practical tips, because these are some commonly asked questions about how to use open source models and when to use open source versus when to use commercial models. So if you have a particular application in mind and you want to try out commercial models, you could do things like prompt engineering, few-shot prompting, chain of thought, and you could also do retrieval augmented generation, because commercial models typically don't allow you to do fine-tuning. But for open models, you can do task-specific fine-tuning as well. You need a little bit of data and compute for this. But in the end, the choice is between how do you balance performance versus cost. Commercial models have a higher general purpose performance, so they are much easier to get started with if you are trying to build a new application. But once you get into production or once you have high volume, open models can beat commercial models on specific tasks with fine-tuning. And typically what we have seen is people prototype with the highest end models, and then once they figure out that this is the task they want to solve, they take open source model like Mistral 7B or 8x7B and then fine-tuning for their task, and this optimizes the performance to cost ratio. We have offices in Paris, London, and in Bay Area. We are always looking for talented researchers, engineers, business marketing people. So please do apply. And thank you. I don't know if you're taking questions, but happy. No. Okay. Thank you so much. Sorry.
Well, thank you. That was awesome. I love using Mistral myself, and I love how it ties into some of those demos we saw earlier in the keynote with Llama File, being able to run this on your own hardware. So props to the team at Mistral for open sourcing all of that hard work, and you can tell it's not cheap to do those things. So thank you very much.
I don't get any signal. Yeah, I grab yours, but I don't think it's because of this. Like, ask them on number 2. Because I don't think he used the same. We need 2. Because that's internet, right? It's like this.
This is 792. There it is.
All right, could you put in
Still screen.
screen? Here. Is it slideshow maybe? Can I do this? Yeah.
All right. All right. Our next speaker is Remy from .txt. Take it away, Remy.
All right. Thank you. So yeah, my name is Remy. I'm the co-author and co-maintainer of the open source library outlines, which some of you might know. And I'm also the CEO and co-founder of .txt or .text, whichever you prefer. We're more traditional machine learning people. And the motivation for work is the very simple observation that large language models are fundamentally flawed. I'll give you a very simple example. You're trying to extract flight information from a bunch of emails. Of course, you want them to be, a JSON object, with origin, destination, etc. So you go to OpenAI, you prompt the model to death, you threaten it, you use function calling, and what you get sometimes as an answer is JSON decode error. I gave you very simple examples, but this has like very fundamental implications because computing rests on interfaces. We're able to build modular infrastructures and very complex infrastructure because we can trust the API over the pieces of code. And here what I'm telling you, and what you've probably witnessed, you can't actually trust large language model to return consistent outputs. And in short is that the technology for agents is currently not there. So the good news is that structure generation, which is the ability of guiding the model to return to the specific structure, actually solves. What we'll see is that it allows you to be GPT-4 as sort of a byproduct. The goals for today are first to introduce the open source library outlines for those of you who don't know about it, then very briefly explain how it works. I won't get into the technical details, and then try to convince you that you should use it today for most of the workflows that you have to deal with, and sort of a very short glimpse into the near future. So outlines is a Python library, emphasis on library. You can actually include outlines in your workflow, and it's not like frameworks where you have to make your workflow, fit inside a framework. I think as a result, it's been adopted by VLLM and TGI in the serving frameworks. And if you use function calling in either of these libraries, you're actually using outlines under the hood. So I'm co-author, but outlines would be nothing without its contributors. Today it's 87. I think it might be 88. I think I merged the PR this morning. I don't remember. And so outlines would be nothing without all these people, and I thank them a lot. People thought we were crazy about a year ago when we were talking about structure generation, but since then, we're pretty happy because it looks like people are sort of caught up with the topic and realize that you can actually do structured output. So just a quick run through outline. So usually generating text happens in 3 stages. The first stage is that you need to choose the model and instantiate it. So outlines is purely focused on open source models. We have integration with 6 different model providers, transformers, Llama CPP, and also recently we added MLXLM. We have an integration with OpenAI, but that's mostly for us to compare the results that we get with open models with the results that are given by OpenAI. The second step is to, generate text. What you do is that you instantiate a generator using generate.text. Here we just want to, return a single sentence. So we're telling the generator stop whenever you encounter a period. And question is described, then you call the generator with your prompt. Here is describe the benefits of structure generation in 1 sentence. And you'll have to wait for 10 more minutes, hopefully less. Okay, now we get into structure generation. So without outlines, if you ask what is the IP address of the public Google DNS servers, and you just generate text, you just let the LLM do its thing, then generally it will yap for a long time, 100 tokens, 500 tokens, and the answer will be somewhere in there. And the way you extract the answer is using regular expressions generally. Here, what you can do with outlines is actually taking that regular expression that you would use to extract the answer and use it to guide the model, to tell the model this is the structure that the output should follow. And as you see, you kind of remove the yapping, you just call generate.regex, call the generator, and what you get is just the result, and it's actually the correct answer. That was with Mistral 7BV01. Regular expressions are not the only way to define structure. Something that people need a lot in practice is JSON. And outlines allow you to generate text that is a JSON object with a given structure. The way you specify the structure is using JSON schema, or you can pass pydantic models as well. Now you might notice on the flight information, so here it's the example that I used at the beginning, you're extracting flight information from an email. I could have used string as a type for origin and destination, but I did not. I use actually a custom type that we implemented in outlines, and the reason is that origin and destination have way more structure than just text. It's actually, it's an airport code that has 3 letters that's capitalized, and you can actually specify more and more structure, all the structure that you have in your problem, basically. You can use this with vision models. That's something that we merged recently. So here we took, I think it's a picture from Wikipedia of a dish. We tell the model what is the JSON that we expect as an output, and then we instantiate the generator, and then pass the image and the prompt to the generator, and we get valid JSON. If you want to install outlines and you think you could benefit from structure generation, then it's very simple. Just pip install outlines. Now I'm going to try to very quickly explain how it works. So models themselves, what Mistral and Cohere of this world are doing, is actually training model weights. What a model does is you input a prompt, you send a prompt, it's like token IDs, and what you get as an output is not text. It's logits, it's a probability distribution over the next token. Now what happens after that, when you want to generate text, the first step is that you have a logit processor that biases the logits. You probably use this every day, actually, without noticing it. When you use temperature, or when you use top K, top P sampling, you're actually biasing the logits. And once you have your biased logits, use a sampling algorithm, then you get a token. And once you have your token, you add it to the prompt and then feed it back to the LLM. And where we fit is here. We actually, whenever the model generates logits, we look at every token and we say, if I add this token to the current generation, is it going to violate the structure? If the answer is yes, we mask it so that it doesn't get generated. Now that story is very simple. What is really hard is doing that efficiently. And that's what we figured out at .text, and that's what makes us different from the other libraries like Guidance or LMQL that do structure generation. And now I'm going to convince you that there's absolutely no reason to not use, sorry for the double negation here, to not use structure generation. The first reason is that most text is structured. I talked to you about JSON earlier. We talked about regular expressions. But here I just took the GSM8K data set. If you look at it, if you're not me and don't structure everywhere, notice it immediately. If you look at the right, you can actually see that it's highly structured. It's always Q, period, text until a question mark, then et cetera, so on and so forth, arithmetic operation, which is defined by a context-free grammar. And you could actually express this in outlines and just get the answer at the end, which is, 6. So there's a lot of structured text out there, not just, thank you. I'll be quick. Of course, the second benefit is that you get valid structure. I mean, that's an obvious one. That's what we're doing it. I like this meme. At the bottom, this is what people are currently doing. It's just crazy stuff to get valid JSON as an output, and it's not even guaranteed. And here, with outlines, you just sample what you want. It's as simple as this. And as an experiment, it's actually an experiment that PrettyBase did. They took Mistral 7BV01. They used a version of CoNNL that they modified so that gives structured output, JSON. What they found is Mistral 7BV01 only gets valid JSON 17% of the time. When you had structure generation on top of it, you get 99.9%, and that's without optimizing the prompt. So you can actually get, you can actually get better than this. The nice thing is that it also adds negligible overhead, so you actually have, you don't have to fear for that affecting inference time, which is the highly non-trivial thing. Here we compared the overhead introduced by Guidance when they do structure generation, as a function of the number of generated token, and at the bottom is outlines. Outlines says approximately 0 until the end. As a trade-off, there's a compilation time, but during inference, it doesn't slow down inference. Now we're at a point where we could integrate this in Grok, and you wouldn't see the difference between structured and unstructured. So no overhead, but even more than no overhead, it is faster to generate text with structure generation. The first is that when you take JSON, you don't need to generate the tokens that correspond to the bracket and to the field names. I know that in advance. I don't need to ask the model to return these tokens. So here on this very simple example, only 5 out of 10 tokens need to be generated, so only 1/2. But there's an even more subtle way in which it accelerates inference. And this is the example that we took at the beginning. So here I asked ChatGPT, like a good model, like ChatGPT, the same question. What is the public, of Google's public DNS servers? And ChatGPT took 50 tokens. It yapped, and gave it after 50 tokens. It's not as bad. It could get a lot worse with lesser models. But when you use structure generation, you just generate 8 tokens. So that's a subtle way in which it accelerates inference by a lot. Then it improves efficiency, and that's probably the most actually mind-blowing result that we've had. So here what you're looking at is the accuracy on GSM8K with, again, Mistral 7BV01, structured and unstructured. And here we look at the accuracy as a function of the number of shots, so the number of examples that you give to the model before asking the question. And what we found is that, yeah, for unstructured, normal, 1 shot is worse than 8 shots. That's completely expected. But what we find with structured is that you actually, and that's really surprised us, is that you actually get in the same ballpark in terms of accuracy with 1 shot as you do with 8 shots, which is surprising for a machine learning person. Like, you would think that examples are there to teach the model about the task, but it looks like it's actually there to teach the model about the structure of the problem. That more investigations to do in this line, but that was very mind-blowing. And the last one, which probably, after faster, a lot of people care about here, is that it does improve the performance of open source models. Here, what you're looking at is the Berkeley function calling leaderboard simple function benchmark, and we'll look at the accuracy. So the first thing we did is that we took Microsoft 3 medium model, which is a small model, but we looked at its accuracy without structure generation. It's 86%, which is pretty good for an open model. 5.3 is actually a pretty good model. When you add structure generation, you get 96.5%. And as a comparison, GPT-4, the best version of GPT-4 on this task gets 93.5% on this benchmark. And now there are two things to note, is that 96.5% gets dangerously close to useful. And the second thing is that we have open models that are available today that can beat, larger models without fine-tuning. So it's a pretty huge boon for open models, and that's why I'm really bullish on open models. I think, as a community, we can actually extract a lot more out of these models. And this is just a glimpse. The work that I just showed you is what we did at .text about a year ago. Since then, we've generalized from regular expression to what you call context-free grammars. Context-free grammars are used to define code. They're used to define protein structure, and to define as well what I showed you earlier on the GSM8K example. So we can do the same thing, structure generation with no overhead with context-free grammar. We also started working on semantics, like adding some semantic constraints to the generation. And one very popular example of this is text-to-SQL. Text-to-SQL, most models that SQL syntax. Usually what they get wrong is they hallucinate table or column names. And internally, we're able to get perfect text-to-SQL. So I can't guarantee you that the query will be correct and give you the answer that you expect, but I can guarantee you that it will run. So that's a pretty huge advance in text-to-SQL. And what else? Oh yeah, and we're also starting to bubble up computations into the structure generation, into the model architecture. Because when you think about it, we're biasing logits. When you're biasing logits, the model is actually doing computation for nothing. And so you can gain even more in efficiency by preventing the model from doing these computations in the first place. And that's all work that we'll actually publish in a blog post, I think, in the next couple of weeks. So all that to say that if you're not doing a chatbot, there's a really good chance that you will be using structure generation. It's just a matter of time until you adopt it, I think. Our users are pretty happy. So yeah, thank you for your attention. And all the crazy claims that I made, you can go, the QR code, there's a link to all the blog posts. Thank you so much.
Yeah, good job.
Oh, it fixed it?
Ready to rock? All right, thanks everyone. Thanks Remy, that was awesome. That was a little mind-blowing that you could go all the way down into the logits and get all sorts of structure and speed out of that. So still thinking about that for days after this. Our next talk is Sandra from Cohere, and I got to have dinner with her last night. She has an awesome podcast on YouTube that you should definitely go check out after this, but excited to hear what they're cooking at Cohere. Take it away. Oh, no. So,
1, 2, 3.
yeah,
All right,
there.
I'm gonna use this one then. Okay, hi everybody. It's my first time at the engineer, and honestly, I'm loving it. On the way from the airport, I came from Warsaw, Poland. I saw so many billboards mentioning AI in it that I really felt like I'm at home. And yeah, just meeting you here and seeing familiar faces and familiar companies is really awesome. It's an honor to speak to you today. So, what if I told you that we have just handed you the keys to state-of-the-art model which excels at structured, advanced RAG, at sequential reasoning, and you can run it locally on your machine. It's competitive against GPT-4 Turbo, Cloud Opus, and it's much smaller. We've been really hard at work at Cohere, working on our family of models, and today I'd like to talk to you about some of the stuff that we've done, the decisions that we've made when it comes to the model design, and also what we're cooking when it comes to the future of the models. So this year we've been working really hard to push the boundaries of what's possible with LLMs, and here's a quick look at our timeline. 3 months ago, on March 11th, we've released Command R. We opened the weights to the model. Command R is a model optimized for retrieval augmented generation, and it's scalable. It's small enough to be scale-friendly. We followed it up with Command R+. And this model is optimized for tool use, advanced retrieval augmented generation, and has become a very popular model in the open source community. Within a few days of the release, we've climbed the LMSys arena. We're really proud of that, really great achievement. Your response as a community using the model has been incredible. Some of the zeitgeist. We started trending at OpenRouter. Within 2 weeks of the release, the model has been downloaded 150,000 times from Hugging Face, which is wild. Folks at Hugging Face actually liked the model so much, especially when it comes to the tool use, that they decided to use it as a base model for Hugging Chat. So now you can play with Hugging Chat. It has a doc parser, an image editor. It even has a calculator. It had it before the iPad. So today, almost 500,000 of developers and researchers are using the R family. We're really proud of that. It looks like you guys got really excited to get your hands on the model and to play with the weights and look under the hood. We keep hearing your feedback, and the love and support keeps pouring in. It really gets us going. And I've seen some super cool stuff built with R+ since then. Some of my favorite ones I want to shout out here are the Coding Assistant by Daniel San and a new generative search demo by Complexity. I'll try to demo it later. We'll see how the tech goes, but I'll give you a sneak peek. Another one that's my favorite is 2 Discord server bots that are powering our Discord community. I invite you to go and check it out. One of them is fine-tuned to be playful and to demo the model capabilities, and the other one is made to be helpful. It's grounded in our docs, and it's focused on the information coming from the API. So I want to share the journey of building the R models, the decisions we've made along the way, and to show you that we've committed ourselves to build the top RAG tools for AI builders. We know firsthand that building RAG is excruciatingly hard, tough word. When you set out to do that, you're going to face challenges, and they are numerous. Challenge number one is that models are highly prompt sensitive, and when you want to use the model in the RAG context, you need to prompt it to not only look for the information, but also know where to look and know how to differentiate between the conversation history that the model has with the user and the retrieved information. It's not a trivial task. Another problem is overcoming models' natural bias towards focusing on the beginning of the document. You've seen it with multiple RAG benchmarks and evaluation tests, needle in the haystack and whatnot, that are really showing the problem of models not focusing on the most accurate information retrieval, but rather becoming a little bit lazy and focusing on the beginning mostly. Another challenge is steering an ongoing battle that's happening within the model between its pre-training knowledge and what it encounters in prompts. For RAG use cases, you want the model to be able to tap into the knowledge that's not baked into the model parameters, and temporal information is a great example. When you're asking the model about who is the current president of the United States, you want the model to be able to tap into the up-to-date information. So through post-training, we've been able to optimize the model behavior to be able to address these and to decide when the external information is needed in the first place. Sometimes it isn't. Sometimes the pre-trained knowledge is enough. Then operate the retrieval system smoothly to be able to run search queries successfully, retrieve the information, hopefully the most accurate one, and then use that information as a grounded context for the conversation that the model is having with the user. We optimize all of this for you, the model behavior, so that you don't really have to think about it. It's really good at it out of the box, but it was hard work. Our major focus was working on citations. We're big on citations. We believe that allowing the user to verify where the information comes from and whether it's trustworthy, it's really important. So we're spending extra time to make these citations very fine-grained, and thanks to that, you can experience low hallucination and reliable context use. We tested Command R and R+ on some standard RAG datasets like KILT, and they exhibit best-in-class performance. They're small enough to be affordable, but powerful enough to cover a lot of your use cases. They have a great balance of token efficiency, and to achieve this level of performance, normally you would have to line up a big pipeline of LLMs. We've also heard from you that creating a UX and UI for RAG and tool use is super painful. It's not a small feat, and we know it firsthand because we've spent considerable amount of time working on it ourselves. We're really proud of it at the moment. I think it has everything a modern UI, modern chat UI needs to have. So you're able to have a conversation history, you're able to have fine-grained citations, you're able to upload documents there, you're able to plug it into different types of tools. So spending so much time on it and knowing how much you're struggling either way, we decided that it's going to be a good idea to open source the UI, and that's what we did in April 24th. I feel like not many people know about it, but our UI is out there and you can download it and start building with it. So this is a toolkit repo, that's how we call it. It has plug-and-play components and source code for an interface app that we've built with Next.js. It has a small SQL database for conversation history. There is a model component which lets you customize how you're accessing Command R models. You can do it via cloud providers, you can do it via Cohere platform, you can do it locally, you can do it via Hugging Face, your pick. Then there is Retrieval component, and here you can customize access to tools and data sources. Out of the box, we've built an example data retriever built off of LangChain. It has document upload, and it's using web search, but honestly, you can add support for any tools and any data sources that you're interested in. Lately, we've been focused on optimizing tool use, particularly in the enterprise context. That's our game. It's kind of extension of this RAG formula I mentioned earlier, where we began by training the models to be really good with vector databases and retrieval systems, and then it naturally progressed into broader tool use. Training the model to use any tools, and ideally in a zero-shot context. That's kind of our ideal scenario that we're working towards. Tool use comes in two flavors. There is single step. It's really useful for situations where you have a single action to be performed or a set of independent actions. It could be searching for a document or sending out an email. Multi-step, on the other hand, it's really good for scenarios where you have to carry out a sequence of actions with each action building on top of the previous ones. So in the same example, it would be searching for that document, being able to compare it against another document, creating a summary of that comparison, and then sending it out via an email. That's possible with multi-step tool use today. In sequential reasoning in multi-step, you want the system to be able to reflect and correct errors if there are any on the way. And we are teaching the models to retrieve the information many times over from these different data sources. It's kind of a loop to be able to do that. You know this behavior from the term agents. Most of the time when people use the term agents and multi-step, they mean the same thing. It's essentially a scenario where software is performing a sequence of actions with each action building on the previous steps. Last week, we released multi-step API, super hyped about it. We wanted to be user-friendly, and so all you need to do is you need to describe the tools that the model has on their hands, what these tools do, and then some parameters. After user request is made, the model is going to create a plan, and it's going to figure out how to use these tools to fulfill the user request. And once it calls each tool, it's going to reflect on the contents, and it's going to adapt the initial plan if it's necessary. So for example, if the model is calling an API and it returns an error, it's going to automatically retry calling it again and coming up with a new plan. We've outlined this behavior in this huge multi-step preamble. You can find it on Hugging Face. Essentially, it's a massive prompt that explains the model what it needs to do in order to get the job done. Unique advantage here is the transparency. We've trained Command R and R+ to generate claims that are verifiable through citations. And again, big on citations, we really believe that when you can explain which tool has been used by the model for each response, it's going to make a difference and it's going to make the system better. Command R+ has competitive performance to Claude Opus, GPT-4 Turbo, but it is 3 to 5 times cheaper. So that's a massive difference when it comes to scalability and being able to use it in production. We test the R family on standard complex reasoning benchmarks, and Command R+ is close to or on par with GPT-4 Turbo. I'm super excited for the upcoming releases. We're gonna keep hammering on the multi-step, and yeah, stay tuned. Thanks a lot.
Can we turn the mic, or here, I'll give you this one.
Sometimes I can demo. I still have 2 minutes, so I can do a demo if you're interested. All right, let's do it. So this complexity, this is this new generative search engine I mentioned. It's just a demo. It's super simple, but it's fun. You can find it at this CPLX AI. And let's see, how do I get better at speaking? And here you're going to achieve the answer that's grounded in multiple sources. Sources are outlined here, but also you can click on particular information taken from particular website and yeah, and go and verify it. This looks pretty trustworthy to me. Anyway, so that was complexity. We also have this internal rack demo. Where was it? I had this massive prompt. Oh, okay. So we're gonna give it a really hard task. What are the 3 largest companies in the world in terms of the market cap? How many employees? Create a graph, draft a tweet. Let's see. As you can see, you can check out the model behavior step by step. So first it's going to search for the companies, then it's going to search for a number of employees, and now it's running Python to create a graph and adding citations. Wonderful. And now we're waiting for the tweet, I guess. Is the tweet coming? It might not. Okay, well, I had to prompt it again, but anyway, you get the picture. So yeah, that's what we're doing now. And then you can find our support and play bots on the Discord server, so go check it out. Let's ask, is the AI engineer happening now? Conference. Well, AI engineer can be happening, but who knows what it is. Okay. Well, that's a bummer. We don't like this answer. Okay, it found other conferences, so it didn't find a engineer, but you can have a conversation with it. It's going to be a multi-turn. It's going to remember the context, and you can push it. Let's try again. A engineer, bro. Nope, no luck. Anyways, you can poke it. It speaks multiple languages. It speaks my native Polish. It's really fun to play with. Oh, yes. Yes, success. Thank goodness. Okay, wonderful. Yeah, so go and play. Have fun. Thanks a lot once again. Enjoy the conference.
All right, that concludes the morning session for open models. Feel free to join us in the afternoon. We have Liquid, AI, Unsloth, and one more that I should know off the top of my head, but they're all going to be great. So see you back here at 2.
is how we grow. Gotta give it up sometimes, let's go. And knowing when to kill your pride. There's no one to blame. Nothing really stays the same. This is how we grow. Sometimes we hold on to let go. Sometimes we hold on to let go. Sometimes we hold on to let go. There is nothing lost between us. And oh, I know you have your reasons. Some days I'm a mess, but I know there's a rainbow over all of the past. Your head on my shoulder, but I know we're better on our own. But this is how we grow. Gotta give it up sometimes, let's go. And knowing when to kill your pride. There's no one to blame. Nothing really stays the same. This is how we grow. Sometimes we hold on to let go. that open for us in a moment. Keeping the light on, right in our old wrongs. Keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over us, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. See in the forest, for the trees I'm keeping watch. All that is storming, waking up and turning on, keeping the light on, righting all the wrongs, keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over us, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. Chasing the light is all we know. Can't stop and I won't let it go. Chasing the light is all we know. Can't stop and I won't let it go. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see We got an insomniac with eyes wide shut, and we got everything we need and then a little too much. I know that you're starving for something you can't touch. Would you be honest with me right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it taking over your senses? Don't you ever fear it? Technological advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Think there's something in my bag that's weighing me down. Oh, it's just the weight of the world. Now I'm calling it out. We're a little starving for some lightning love. Can we speak honestly right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it taking over your senses? Don't you ever fear it? Technological advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. wanna be next to you. You wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. You wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. some luck. Can't find a door that's open. I'm losing all my hope. Feels like I'm left here in two because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. missing you. I was chasing all the wrong signs, trying to hold on to something that I couldn't find. Wish you didn't captivate my mind. Now I know even the sunsets in paradise, but now something went wrong. You're moving on. I found myself on the blind side. Now you won't call. We lost it all. You fade away. I'm picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck, can't find a door that's open. I'm losing all my hope, feels like I'm left here in two. Because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. Picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck, can't find a door that's open. I'm losing all my hope, feels like I'm left here in two. Because I'm missing you. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll dive in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll dive in and I'm ready to whoa. We are a summer storm, a feeling you can't ignore. Do you ever stop to feel it caught in the afterglow? I'll come back to your door to know that you believe it. In summer, all that I want, you know, summer we got it all. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll dive in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll dive in and I'm ready to whoa. We'll light it up again, the sky and our silhouettes, dancing on the pavement, caught in a perfect storm. You and those eyes again, caught when I least expected. Said you're all that I want. We know together we got it all. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll dive in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll dive in and I'm ready to whoa. If I find myself at your door, would you follow me to better places? If I find myself at your door, grab the keys, let's go. I wanna taste this. If you showed up at my door, I would follow you to better places. If you showed up ready, let's go. Ready, let's go. Oh, holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll dive in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll dive in and I'm ready to whoa.
Check 1 2. Check 1 2.
So I
Check
could
1
find
2.
strength to divide us.
You have.
Gave it all we got, and I know we did the best we could. If I could go back, undo the mess, I would memorize your face before I go. But this is how we grow. Gotta give it up sometimes, let's go. And knowing when to kill your pride. There's no one to blame, nothing till we know. Doors that open for us in a moment. Keeping the light on, righting our old wrongs. Keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over us, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. See in the forest, for the trees I'm keeping watch. All that is storming, waking up and turning on, keeping the light on, righting all the wrongs, keeping our sights on everything we want. We catch our breath in the middle of it all, chasing echoes. Sun is coming up over us, it's coming. Crystal vision. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. Chasing the light is all we know. Can't stop and I won't let it go. Chasing the light is all we know. Can't stop and I won't let it go. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see on the horizon all our hopes. We can feel it, chasing the light is all we know. Like a fever, burning up, yeah, we're on fire. True believer, we're walking on the wire. I can see something you can't touch. Would you be honest with me right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it? Taking over your senses. Don't you ever fear it? Technologic advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Think there's something in my bag that's weighing me down. Oh, it's just the weight of the world. Now I'm calling it out. We're a little starving for some lightning love. Can we speak honestly right now? There's something in the undercurrent, I can feel it coming up. Don't you wanna feel it? Taking over your senses. Don't you ever fear it? Technologic advances. Baby, come escape with me. I'll come sweep you off of your feet. Don't you wanna feel it? Don't you wanna? Don't you wanna? Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. Tell me that you wanna stay. Baby, just don't walk away. I need you now. Fade it out. All the time we spent alone, fighting through the firestorm. Don't let me down. I need you now, 'cause I'm feeling worn out. It's getting to me. Lost some heart trying to get on my feet. Caught in the madness, I feel you somehow. Don't let me go, I need you right now. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you, you wanna be next to me. Holding our paper hearts, fading our broken dreams. I wanna be next to you. for some luck. Can't find a door that's open. I'm losing all my hope. Feels like I'm left here in two because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. Because I'm missing you. I was chasing all the wrong signs, trying to hold on to something that I couldn't find. Wish you didn't captivate my mind. Now I know even the sunset's in paradise, but now something went wrong. You're moving on. I found myself on the blind side. Now you won't call. We lost it all. You fade away. I'm picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck. Can't find a door that's open. I'm losing all my hope. Feels like I'm left here in two because I'm missing you. Because I'm missing you. Oh, because I'm missing you. Because I'm missing you. Because I'm missing you. Picking up my heart from every piece that's broken. Been trying to get back to myself, but don't have a clue. I'm looking for some luck. Can't find a door that's open. I'm losing all my hope. Feels like I'm left here in two because I'm missing you. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll tap in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll tap in and I'm ready to whoa. We are a summer storm, a feeling you can't ignore. Do you ever stop to feel it caught in the afterglow? I'll come back to your door to know that you believe in summer all that I want. You know, summer we got it all. Holding my breath and I'm ready to go. I'm falling right in and I'm ready to go. I found what I want and I know that we're on top, so I'll tap in and I'm ready to whoa. Holding my breath and I'm ready to go. I catch you laughing and I'm ready to go. You're holding the match, strike it and ignite my soul. I'll tap in and I'm ready to whoa. We'll light it up again. The sky and our silhouettes dancing on the pavement.
And I think the timer's already running just because we're a minute late here. Okay, cool. Cool. Want to go full screen and I'll introduce you? All right. Check 1 2 1 2. Ready to go on this one? This mic. Check 1 2 1 2. Testing, 1, 2. Testing, 1, 2, 3. Should I just go this mic? Is this one working? All right, there we go. Welcome everybody to the second half of the day on the open models track. We've got a great lineup for you. We have Leo from Gradient. We'll have Daniel from Unsloth right after this. And then last but not least, we'll have Maxine from Liquid AI. So excited to hear about the fine tuning and the finance use case. Hand it over to you, Leo.
Cool, thank you. Yeah, hi everyone. I'm Leo, I'm the chief scientist at Gradient. And today I'll be talking about how we trained large language models to be finance experts. Yeah, let's go ahead and dive right into it. So before I start getting into the details here, I wanted to make a couple of observations. And the first one is that foundational models have been growing at an exponential rate, right? So not only do kind of bespoke AI companies each have their own foundational models, but data companies, general tech companies, they all have their own flavor of a language model, each with its own features and use cases. And another observation, which is pretty related, is that the context length, right, the number of tokens that you can fit into a prompt has increased quite a bit over the past year. The largest context length models about a year ago were something like 100K, and in the past year they've grown to about 40 times that, just in models released in the past few months, including one released by Gradient. And both of these observations are evidence to kind of one point, and that's that large language models are not one size fits all. Especially when you get to kind of more complicated use cases, taking a generalist language model or a base language model kind of off the shelf isn't really going to get you too far. And I realize I'm talking at the open models track of a conference. I probably don't need to convince you guys too much of this statement. But it is pretty important for us at Gradient. It was actually our foundational thesis for what we built, which is an AI foundry. And for us, what an AI foundry is it's a collection of, sorry? Okay, it's a collection of a number of custom language models. Yeah, except this guy's a little touchy. There we go. Stand over here. Collection of custom language models, as well as a number of workflow primitives. And what we do is we take all these pieces and components together to create solutions that are a custom fit for our customers. And today I'm going to talk about specifically our solutions for the finance domain, right? Building financial experts. And for those solutions, really two components have been incredibly useful. One should be fairly straightforward, is our domain-specific finance language model, and the other one is a context length extension that we've worked on. And so why are these important specifically for finance? Well, a little while ago, we got together and wrote down kind of 6 requirements for finance applications of language models that generalist models tend to lack or fall a bit short on. You know, if you look at these requirements, they're fairly general. They kind of apply across industries, but in particular for finance, they seem pretty important. And today I'm just going to talk about 2 of them that happen to be paired with the 2 solutions that I also want to talk about, the finance language model and the extended context length. So jumping right into it. The first one is the finance language model. You know, you might be wondering why even have a domain-specific language model? Why is domain knowledge important? The reason is that your general-purpose language models, like the GPTs of the world, they are trained on a very broad set of data. Kind of broad, not deep, especially in kind of like more technical situations, like technical financial information. And as kind of like an illustrative example on why this is important, here's a chart from a recent research paper, and it shows that even for very large models, right, the red line at the top there is for a 176 billion parameter model. you need something on the order of thousands of relevant documents in the model's pre-training in order for the model to get decent, I mean, here it's even above 50% accuracy on answering a related question, right? And so kind of what this implies is that if you ask a language model questions about data that's kind of like in the tails of its training data, then it's going to do a poor job at answering those questions, right? And so, you know, the natural way to fix this is to say, okay, base model doesn't know a lot about finance, let's train it some finance. An issue there, and here I'm going to talk about kind of how we trained our finance-specific language model, is, so an issue there is that there's a whole lot of financial data out there, right? Like way more than you could possibly review or look at manually. And so that requires creating an automated data pipeline. And that's what we did. We created one. Probably the most compelling or interesting part of this data pipeline is the automated data curation, where we borrowed ideas from the membership inference literature. And so what we do is we amass a whole large corpus of training data. And then we use techniques to try to see if a particular document, if there's a high chance that it was already in the model's training data, right? So maybe you have like a llama-based model, you have a document, and you can run some of these techniques to get a probability of whether or not the model has already seen that data in training. So you filter out all the data that the model hasn't seen before. What you're left with is a much smaller set of data, now that's manageable to look at through human review, and then finally pass through to synthetic data augmentation, right? Both to upsample data and to handle some variations in data representation and formatting. And kind of like the last part of the recipe for how to train domain-specific language models is to take that data set that you created and to pass it through a training pipeline. I think by now a training pipeline like this is fairly standard. There's two main parts. One is the continuous pre-training. So you take that data set that you created on the previous slide, and you do kind of next token prediction on it off of a base existing model, right? So again, we're taking a base foundational model like a llama model to start with. And then the second part is you run alignment on the model. Here we ran both supervised fine-tuning and preference optimization. And kind of the way I like to think about the division between these two tasks is pre-training is something like if you had a bunch of textbooks and you wanted a model to read all those textbooks and understand all that information or retain all that information. And alignment is kind of like then instructing the model on how to use that information or best practices and what to do with that. And so if pre-training is like reading textbooks, alignment is like maybe like taking an exam on a class or working on a project. Right, and that's really all I wanted to say about the domain-specific language model. Now I want to talk about see how much time I have, great. About the other part, which is the extended context and how extended context or long context language models help us address hallucinations. Right, to give a quick refresher, what are hallucinations? Well, it's a pretty broad term, and it's used quite frequently nowadays. It's whenever you run inference on a model, when you give it a query, and it generates content that is irrelevant or made up or inconsistent with the input data. There's been a fair amount of research as to the cause of hallucinations. A lot of that research points to deficiencies in the underlying training data. Right, so some causes might be just the training data is outdated, right? You're asking the model a question on information that is now updated since the training data. Another one is a lot of the training data practices require automated data collection, and if there's ever inconsistencies or bugs in that data collection, you can get source reference divergence, right? So the model is just trained on data that doesn't quite make sense. And there's a few other reasons. All of these can encode information in the model's memory banks that isn't quite accurate, and that'll cause the model to hallucinate. And while alignment or continued training of the model can alleviate hallucinations. At Gradient, we find that actually in-context learning, so working directly on the prompt during the execution pipeline is the most direct and sample-efficient way to reduce hallucinations, right? Because what you can do is you can put in a relatively small amount of information directly into the prompt, kind of at inference time, and sort of plaster over or band-aid over issues with the model's training data. And so that's great. In-context learning works really well. The issue is it works so well that when you start doing it, you want to do more and more of it, and then kind of you run into one of the biggest pain points with this practice, or one of the biggest bottlenecks, which is the context length. And I'm guessing that this is an issue that many of you in this room have come across yourselves, and that's you just run out of prompt in terms of for in-context learning. A few examples for why that can be an issue. If you're trying to put in few shot examples into the prompt, you run out of prompt space before you run out of examples, so now you have to spend a lot of time in choosing the particular example or working on some kind of like lossy summarization technique. For more complex problems, they may require some brittle pre-processing pipelines. Each can have errors. And also if you do some kind of external memory management such as RAG, those systems tend to have poor performance when the chunks that get pulled require them to be interrelated, right? So if you pull one chunk and another chunk that you need to pull has to reference a previous chunk to know if it needs to get queried, right? And RAG typically does a pretty poor job at that. Right, so context length is the bottleneck for this, so the most natural thing to do is just extend the context length. And so that's what we did with some of our models. And here, really, I just wanted to talk about a couple of examples of what suddenly becomes possible when you have a context length that's sort of in the realm of 1 million tokens long. Here on the left-hand side is an example showing that you can now actually put thousands of examples directly into the prompt. And that kind of gets you back into this kind of like domain learning regime that I talked about earlier. It's just now it is on the fly and at inference time, right? So it can be very adaptive to the problem. And you do find that for a lot of tasks out there, this like thousands of examples mark is actually necessary to get kind of production grade accuracy or dangerous levels of accuracy for a model. And the other example is with a long context length, you can leverage what transformer models are natively really good at, which is being able to attend to every single token in the prompt. And by doing that, you can actually have the model perform fairly complicated reasoning implicitly, just through going through its layers and attention layers. And an example that we kind of cooked up in-house was we took books that were written by Mark Twain, the author, and first we scrubbed the books of any kind of identifying information, right? So no mention of the author or anything like that. And then we gave that into the model, into its prompt, into its context, and asked the model to generate new stories in the same style. And after kind of 5 books of reference prompts, the model was able to generate stories that convinced a separate critic model that those short stories could have been actually written by that same author, right? And in pretty actually like deep and intricate ways, not just kind of like stylistic similarity or language, but down to theme and characters and setting and things like that. So kind of the punchline is that long context language models give you more grounded and robust systems, and there's fewer moving parts. Much more is contained in the language model, which is the thing that we all care about, and that in turn reduces hallucinations. Right, so you know, those are basically the two components, two solutions of our platform that I wanted to describe to you all today. One of the things that we believe in pretty strongly at Gradient is to have transparent and verifiable benchmarks. And also we're pretty passionate in giving back to the open source community, because a lot of what we've built our work on are open source models and techniques themselves. And so for both of those solutions, we've open source models on our company page at Hugging Face. One of them is the V Alpha Trust model. So that's the result of applying our finance domain training on a Llama 2 base model. And here the benchmarks show that after doing that, it ends up being competitive and actually better, competitive at kind of open LLM general benchmarks and better at finance-specific benchmarks to models in the same class, to its peers. And the other model is a 1 million context length extension of a Llama 3 base model that we released pretty recently. And with it, we were able to get 100% needle in a haystack scores, actually above 1 million context lengths. That's the first image. And also had a pretty substantial performance improvement over the base model on a ruler long context length benchmark. That's a benchmark put out by NVIDIA. And that brings this model kind of in the realm of flagship long context models like Gemini 1.5 Pro, GPT-4, and Command-R+. Right, and so these models are open source, publicly available. I invite you all to go and check them out. And I have about a minute left, so I'll finish off here. There's of course lots more to building an AI financial expert. These are just two pieces of the puzzle, even though they're two important ones. And if you guys are interested in finding out more, feel free to check us out on our website or reach out and contact us. Cool, thank you.
All right. Testing, 1, 2, 3. Good to go. Thanks, Leo, for that. Next up, we have Daniel from Unsloth. And contrary to the name of Sloth, you guys make LLMs really fast. Am I right?
Yes, exactly.
All right. So looking forward to the technical deep dive we have here. And my company's also named after an animal, Oxen.ai, so a slow animal too. So here's to slow animals and LLMs. Okay, wait, do we do one more in here? Okay, yeah.
Oh, this. What is this? It's like a. Do we need to do this? Okay.
You're going to stay at the podium, yes, sir?
Yeah.
On this mic.
Oh, okay. Okay. Hello. Okay. Hello. Hello. Okay. Yes, that works. Oh, okay. Wait, it's already starting. Okay. Okay. Ooh, that's not bad. Is that not working?
Do you want to email me your slides real quick?
It's called tinyurl.com/unsloth2. I can give it. It's weird. Sorry, some technical difficulties. Yeah, /unsloth2. Oh yeah, that. Do we need to find that?
Oh, you need that adapter. Or is there one on that side?
Yeah.
Okay. Let's go on this side. Do you see it?
There we go.
Oh yes.
All right.
Okay. Thanks.
Got it.
Yes, hello everyone. So today I'm going to talk about how to fix bugs in open source models. Thanks for coming again. We had a talk yesterday, the 3-hour workshop, and thanks for coming again. So we have slides. It's at tinyurl.com/unsloth2. For the workshop slides, which we did yesterday, you can also access that now, tinyurl.com/unsloth as well. So you might know me from like the Gemma bug fixes that we did. So Gemma was an open source model by Google, and there are like a few bugs in there, and we fixed a few of them. And we just did some tweets about this, and like there's many bugs in there, like the activation function had to be approximate GELU, not exact GELU, and there are some other issues that we talked about for Gemma. We also have like a few stickers which you can get them from like when we're outside, but this is, yeah, we won't be handing them during the talk, but yeah, they're very cool and cute. And also there's like tokenization problems as well in language models, which we also help to fix. Today, I'm just going to be talking about Llama 3 bugs. So yesterday I talked about Gemma and V3, and today we're just sharing all the stuff that we found with Llama 3. For Gemma, you can access like all the bug fixes that we did in our blog post, and we have a Colab notebook for all of the Gemma bug fixes as well. For V3, for example, we talked about this yesterday, and I just pasted some slides again if you want to like review this in your own time. For example, like the sliding window should be 2048, not 2047. You can also you should unfuse all of the QKV matrices, otherwise LoRa fine-tuning will not work that well. But we'll be talking mainly about Llama 3. So there's actually 8 bugs in Llama 3. Some of them are not announced yet. We will be announcing these later. So this is like a pre-release. And we'll be going through each of them separately. The first one is you must not use double BOS tokens. So this is actually a very common theme in fine-tuning Llama 3. Some people don't actually know that you're adding 2 beginning of sentence tokens to the fine-tune. And this will actually ruin your fine-tune by making the accuracy of your inference time lower. So please check before you fine-tune if you're using double BOS tokens. In Unsloth, we do this, we check this automatically, and we'll remove the extra BOS token automatically for you. So this will actually cause your model to lose accuracy, because if you trained on 2 BOS tokens and you do inference on 1, then your model template will be incorrect. So please check this. It's not just a Llama 3 problem. Other models like Mistral and Gemma also have problems like this, so just be careful of this issue. So a very easy way to check if you have double BOS tokens, if you use the apply chat template from Hugging Face. If you do the first one, your chat template must have a BOS token, otherwise it won't add it. Llama 3 does require a BOS token. If you do the second one, you're actually having 2 BOS tokens if you do this, so please do not add a BOS token to the chat template. The second issue we found was you must not use the Llama 3 base model if you're using the Llama 3 template. There are some untrained tokens in Llama 3 base. The instruct version actually has these tokens trained. So please be careful when you want to use the Llama 3 base model when you want to do your fine-tuning, because some of these tokens will cause nans for your gradients. These tokens include the reserved special tokens from 0 to 250, the end of turn token, the start header, and the end of header. And the graph I showed shows you the mean of the embeddings versus the other tokens, and some of them actually are 0. So the Llama 3 team made some of these tokens go to 0 purposefully, because these tokens are not actually used for the model. So just please don't use some of these tokens when you do fine-tuning as well. If you want to fix them, set them to the mean of the entire tokens. And in Unsloth, we do this automatically as well for you. So we showed some code where you can take the mean of the trained tokens and set them for the untrained tokens. Just be careful, don't do this incorrectly as well. If you want to take the average of all the tokens, don't just take the average, you must remove the untrained tokens from the average. If you do not do that, you might actually have an incorrect average, right? If there's 10,000 tokens which are untrained, if you divide it by 10,000 plus the number of trained tokens, your average will be incorrect. So you have to do this more complicated method of masking out the untrained tokens and then take the average. Also, reminder, because of this issue, the Llama 3 chat template will not work for the base model. I have known that many fine-tuning people have used the Llama 3 instruct chat template for the base model, and your fine-tune will actually be incorrect. you will get nans in your gradients, and your whole fine-tune will be broken. So please do not use the Llama 3 instruct chat template for the Llama 3 base model. Only use this for the instruct model itself. Another way to fix this is to actually train the LM head and the embed tokens, which will actually learn and remove the nans in your models. Another interesting fact, and not just a Llama 3 problem, but for other models, is the pad token and the EOS token must not be the same. If you do this the same, your model will have infinite generations. The reason is because the pad token gets masked out during the error, during the cross-entropy loss. And if you use the same pad token as the EOS token, then your EOS token, the end of sentence token, will be masked out. So just be very, very careful when you do fine-tuning to check what is the pad token ID and the EOS token ID. For example, if you look at feed 3, they're the same. So technically, feed 3, when you do fine-tuning, it will be infinite generations. So just be careful and look, before you do the fine-tune, check what is the EOS token and what is the pad token. They must be different. For unsloth, we also do this automatically. We fix this for you, and we essentially check if there is any unreserved tokens, and we just select one which is untrained. If there is no untrained tokens, then we will add an extra pad token ourselves. Be careful, do not add a pad token which has the same vocabulary as your current vocabulary. So what we do is we actually check the tokens inside the vocabulary and add extra hashes to see, to make a new pad token. Another issue we found for fine-tuning people is when you finish your fine-tune, you don't actually know how to export it to Olama, and that is because the chat template for Olama must be exactly the same as your fine-tune. And this was actually very complicated to do before, and now we can actually automatically generate the model file for you during the fine-tune. So we have 2 Colab notebooks for you to use for Olama. One of them is the alpaca dataset, and one of them is you can upload a CSV file to make Olama work after you finish fine-tuning. Now, there are some community contributions for Llama 3 bugs. There is 3 of them. The first one is someone noticed that you can only use CPU conversion and not GPU conversion when you convert to GGWAF or Llama CPP. So be careful when you convert to Llama CPP that you must use the CPU version. I think the main reason is because the precision is different in a GPU than a CPU. The CPU, when you do float 16, it's different from when the GPU does float 16 conversion. So just be careful on that as well. Another issue is, remember we talked about the WBOS tokens? Through our community contribution, Llama CPP now has a warning for you to tell you that you're using WBOS tokens. So please, take heed of the warning and do not add WBOS tokens to your chat template and when you do inference. Another point someone found was adding a system prompt could make fine-tuning much better. And so sometimes when you do inference on Llama 3 instruct, if you add an actual system prompt, this could make your whole fine-tuning better. I think for some people, when they add the system prompt, you actually miss the system prompt, you don't actually add one. And so maybe try your fine-tune with the system prompt. And you never know, this could work. So we have a GitHub package, which is open source. And you can click the button Start Free Fine-Tune to start your first free fine-tune using unsloth. We already pushed all the Llama 3 bug fixes to our GitHub repo. And so the Start Free Fine-Tune button will redirect you to a fixed Colab notebook for all of these issues. Feel free to star us as well. We also have a Discord channel, so if you have any questions, you can ask any question that you like about our, how to do fine-tuning, talk about AI, and talk about our bugs as well. We also have a blog post, so blog posts about all our fixes, about Gemma, Llama 3, Phi 3, and more. For example, we talked about continued pre-training. You can do continued pre-training using unsloth now. You can train on the LM head and the embed tokens. And we show that instead of just training like that, you need to reduce the learning rate of the LM head and the embed tokens by 10, or maybe 5 to 10. And this will make your training much better. We also support 4 times longer contexts using unsloth. And this also does not increase the time of completion. So we make it 1 to 2% slower, but you get 4 times longer contexts using unsloth. And this was because we use something called offloading gradient checkpointing, where we offload the gradients to system RAM. There are some other systems which offload the gradients to the disk. Please do not do that. If you offload to disk, then your time of completion of your fine-tune will be extremely slow. So try to offload to system RAM first, and then offload to disk. Although if you offload incorrectly, you might actually make this slower as well. So your offloading must be non-blocking calls, and do not do blocking calls to the system RAM. Yeah, so I will show you, okay, let's see if I can open up, let me go to, does this work? Okay, I'm gonna open up a Colab notebook for the Olama one. Yes. Okay. So for the Olama Colab notebook, you can simply just install Unsloth over here. This is already for free for everyone to use. And essentially, don't forget when you do the Colab notebook, you have to select a max sequence length. This determines how long your model wants to do long context fine-tuning. You can set this to any number that you like, but remember your data set must match the max sequence length. So for example, if you want to set the max sequence length to be like 10 million or 1 million, but your data set is only like 1 million tokens or like less, try to like not set that max sequence length to be that large, otherwise your model cannot do fine-tuning on long sequence. Load in 4-bit does 4-bit training, so this actually reduces memory usage by 4 times. If you do it to false, your memory usage will explode, so please do not try false, especially on a free Colab Tesla T4. If you do false, your memory usage might skyrocket to 16 GB, so do not do that. You only should do this if you use more stronger GPUs. We support, like Unsloth supports fine-tuning all models including like Llama, Mistral, Gemma, V3, and more. So this area, like the model name over here, you can actually try to select any model name that you like. I don't think that people know that Unsloth can support other models other than the ones we listed. So please try to put any model, like a Hugging Face model name in there, and it should work. So for the get PEFT model, this is where you add the PEFT LoRa adapters. The R is the rank. So we set it to be 16, but you can select any number that you like for fine-tuning. So we suggest you normally to use powers of 2, but you can use any number, like 1, 2, 3, like any number that you like. The larger the rank you select, you can make the model learn more about your data set. So, but if you add too large of a rank, you might actually overfit your data set, and also your memory usage might skyrocket again. So we normally suggest people to select 16, 32, 64, or 128. Try not to select too large ranks. The maximum rank you should select is the size of the dimension of the model itself. So if it's 4096, set this to be 4096. For the target modules, be careful. You must do fine-tuning on all linear layers, right? So Q, K, V, O, down, up, and gate. Some people have done fine-tuning without doing some of these layers. Please do not do that, because this will cause your fine-tune to be not optimal. And the LoRa alpha, there is actually a trick for this. Normally speaking, select the alpha to be the same as the rank or larger. We found that if you do 16 times 2, so the rank times 2, this can make your fine-tuning much better. You can also use RS LoRa to be true to set the rank automatically for you, to set the alpha automatically for you. For the gradient checkpointing, Unsloth is the method which we showed that you can do long context fine-tuning. You can also set this to be true, but your memory usage will increase again. We also show you how to do data preparation in a Olama Colab notebook. So this one is we upload a Titanic CSV. So the Titanic dataset, the goal was, can you predict if someone died or survived if you're on the Titanic? And you get details about the person, for example, their age, their like fare, where did they embark from, and so on. With our new Colab notebooks, you have to be very careful when you do Olama chat templates, because when you do fine-tuning, you can only have 2 columns, the instruction and the output. But what happens if your CSV has more than 2 columns, the instruction and output? What we can do is you can merge the columns into 1 column, and with Unsloth now, you can actually do that. You can merge the columns into 1. And also, we show you that you can do customizable chat templates now. So previously, if you want to do an alpaca-style fine-tune, you have to use instruction, input, and response for the alpaca-style fine-tuning. But remember, the problem is, if you want to output to Olama or ggwef, you can only have 2 columns, the instruction and output. Right? If you do ChatGPT, you have to type something, and then the output comes along. You can't have like 3 inputs, right? So what we do is you can actually customize your chat template, and you must include the input and the output, and you must do this repetition twice. Some people have asked me, like, why do you have to do 2 repetitions of this chat template? It's because there is dangling new lines, And we found a solution to this is you have to specify 2 iterations of your chat template. We also show examples of how to do the Llama 3 chat template using our methodology. So you can see there is 2 iterations of the chat template. Reminder, if you don't use the 2 iterations, you will error out. And this is the training methodologies. We normally suggest people to use a batch size of 2, gradient accumulation of 4. Remember, the memory usage is only relevant to the batch size. So try not to set the batch size to be very large, otherwise your memory usage will explode. Instead, set your gradient accumulation steps to be larger. So the formula for the effective batch size is batch size times the gradient accumulation. So in this case, it's 2 times 4, which is 8. Set your learning rate to be 2e minus 4 or smaller, maybe 2e minus 5. And after that, you can also do inference on the model. So now you have to use the apply chat template. Remember, be careful of double BOS tokens, but we in Unslot fixed this. And finally, you have to save this to Ollama. And you have to install Ollama first. We now support saving multiple ggware files. So you don't actually have to save it to 1 ggware file, you can save it to multiple. And we actually allow you to do this now. Before, if you want to save to multiple ggware files, you have to wait 10 minutes extra. You can now do this automatically by specifying more than one format. We also can show you the model file which we created. So you can actually copy paste the model file and put this to like a custom Ollama as well. So the model file was the complicated part when we had to automatically generate this. So we have like internal code to generate the model file automatically. And finally, when you want to do inference, you can do Ollama to do inference. And it works in general. So try that out. The Ollama chat template notebook is in the slides, so tinyurl.com/unslot2. And remember the workshop slides, which we did yesterday, is tinyurl.com/unslot. And don't forget to join our Discord channel. If you have any questions, I'm outside. You can ask questions and stuff like that. And yes, thanks for coming. I much appreciate it. Thanks a lot.
All right. Thanks, Daniel, for all the hard work finding those bugs. You're really getting under the hood there. I'm excited to try it on my own. I have a little 16 gigabyte GPU that this will be fun to play around with. All right, next up, we have Maxime from Liquid AI. You ready to rock, Maxime? All right.
Where's the HDMI? Okay. Should I speak here?
Yeah, it'll be this one. You have to plug this side in too.
This? Okay. Okay. Hi everyone. Can you hear me well? No. Yeah. Is it okay now? Cool. Hi everyone. In this session, we're going to talk about everything you need to know about fine-tuning LLMs and model merging. Quick intro, my name is Maxime Labonne. I'm a staff machine learning scientist at Liquid AI. I'm also a Go developer expert. I write blog posts on these topics. I created the LLM course, which is super popular on GitHub. I also contributed to the open source community through models, through tools, and I'm the author of hands-on graph neural networks using Python with Pact. So first of all, let's talk about fine-tuning. We saw a bit of fine-tuning in the previous session, so I'll try to not repeat too much. But basically, here's the LLM training lifecycle. You see 3 stages. First of all, you have the pre-training stage, where you give a lot of raw text to the model. And the idea is that the model learns to do next token prediction. The result of that is called a base model. this base model is really nice, but if you ask it questions or instructions, it's going to autocomplete your question instead of answering it, which is why we have the supervised fine-tuning stage, where this time we give pairs of questions and answers to the model. And we have a similar training objective, but the idea is that at the end of it, it's going to actually answer your questions and follow your instructions. Then we have a third and final stage, the preference alignment stage, where we give human preferences to align the model to how we want it to behave, and the result is commonly referred to as chat model. So when to use fine-tuning, here you can see a little flow chart that I've made. It's very high level, but basically there's a conversation about when to use prompt engineering, when to use fine-tuning. I think it's good in general to start with prompt engineering if you can, and the idea is to have a really robust evaluation structure where you have a lot of different metrics that you're interested in. It can be the accuracy of the model. Does it answer my question well? You can create a custom benchmark if you have a very niche use case, or you can reuse open source benchmarks. But also in terms of cost, latency, because the question is it good enough? If it's good enough with just prompt engineering, then probably you don't need fine-tuning. The problem is solved. Congrats. Otherwise, the question is, can you make an instruction data set? So can you create pairs of questions and answers to fine-tune the model? If it's not the case, it can be for multiple reasons, but it's probably a good sign that you need to rescope the project. Otherwise, fine-tuning is an option, and you can reuse the evaluation framework that you created to evaluate the model. So that was the technical answer, but you also have a non-technical answer to that. Here's a report from A16Z. And the question is, why do enterprises care about open source? You can see that the two main items are actually control and customizability. And customizability is mostly about fine-tuning models. So even if there's like arguments about the technical side and cost and latency, there's also like a strong argument for customizability and control over these models. So in terms of fine-tuning libraries, I think that you know about Unsloth now, but I'm going to talk about the other ones. So TRL from Hugging Face, a great library built on top of transformers, very easy to use. You have Axolotl, excellent library, very versatile. You have a lot of YAML config files, and then you have Llama Factory, where you have a really good graphical user interface that is built in. So to talk a bit more about supervised fine-tuning, here you see an example of a sample that we give to the model. So we have the instruction, which is both the system prompt and the user prompt, and the answer, which is the output. So in this case, the system prompt is used to steer the behavior of the model. Think like you're answering to a 5-year-old. And the user actually gives the task, remove the spaces from the following sentence. We train the model usually, like generally, on the output only, so we mask the rest. It's used as context, and what we want to do is train the model to output the correct answer. Most SFT datasets, I want to say that use synthetic data, and that's perfectly fine. Usually it's generated with frontier models, and that's a great way of building higher quality datasets. Then you have the preference alignment. I'm just going to mention it here. There are a lot of different methods, PPO, DPO, KTO, IPO. In practice, direct preference optimization is probably the most popular one. So here you see that you have a different format with an instruction, and you have a chosen answer and a rejected answer. So the idea here is that you're going to show like a positive example, negative example to the model. And with DPO, the goal is to make sure that the model that you're currently training outputs higher probabilities for the chosen answers than the untrained version of the same model. I'm not going to delve too much into the details here, but this is the general idea and can be used to either censor the model, how to make a bomb. The chosen answer would be, as an AI assistant, I cannot tell you that. Or it can also be used to boost the performance of the model in general. How to create SFT datasets. So this is a very fundamental question in the post-training world. And the main question is, okay, what's a good sample? Human evaluation is quite bad at actually reviewing the samples, but what I like to define is like 3 main features. The first one is the accuracy. We want the samples, the outputs, to be factually correct. Maybe no typos would be good too. We don't want to compromise the knowledge of the model by giving it fake information. Then you have diversity, and diversity you want to cover as many topics as you can. Of course, it depends on your use case, because if you do summarization, you won't be as general as if you do general purpose fine-tuning. But it's always a good idea to include a lot of different topics, different writing styles in this data set. And finally, you have complexity. I think this one is a bit less trivial. And it's about giving complex tasks to the model, forcing reasoning. So for example, the output will have chain of thought reasoning because you want to train the model to have this kind of reasoning. Or it can be tasks like summarization, explain me like I'm a 5-year-old. This kind of task really force the model not to only answer the question like a QA with answers you could find on Wikipedia. It also forces it to reason over the prompt and give a more complex answer. So as a little recipe you can see here, I would recommend in general starting with open source data sets if you can, combine some of them, then you can apply different filters. The first one is data deduplication. It can be either exact because you want to remove duplicates. It can be fuzzy, so same idea. And then you have data quality filters. Here you have different techniques. It can be rule-based filtering. For example, you want to remove every single row where you have, as an AI assistant, I cannot, because people hate it. But you can also use more clever techniques like reward models or LLM as a judge to evaluate the quality of each sample and filter out the bad samples. And then you can use data exploration with different tools like Lilac, Economic Atlas, text clustering to have topic clustering to visualize your data set, to get ideas on how to improve it. And with these ideas, you can go back to data generation and start the process all over again. In terms of SFT techniques, we have 3 main techniques. Full fine-tuning, this is like the most basic one. You take the base model and you just train it on the instruction data set. It has the best performance, but is also like very inefficient in general. A more efficient way of seeing it is LoRa. With LoRa, you are going to freeze all the pre-trained weights and you add adapters to each targeted layer. These matrices A and B are these adapters. So you have you don't train on all the parameters of the base model. You only retrain a subset of them. So this is a lot faster, but it can still be costly because you're still loading the entire model in 16-bit precision here. So a more efficient way is to quantize the pre-trained model here in 4-bit precision. This is QLoRa. And you apply the same idea that you had with LoRa, but this time the weights are heavily quantized, so you have a lower VRM usage. But the problem is that it also degrades performance, so there's a trade-off here. I want to briefly mention some hyperparameters, but Daniel already talked about a lot of them, so I'm going to be brief. I think the most important one is the learning rate. The learning rate is model dependent. It requires a few experiments to be able to really tweak it and find the best one. Generally, I would recommend to go as high as you can until your loss explodes, like in this graph. Then you can reduce the size of the learning rate. Other super important hyperparameters, number of epochs. I would say that depending on the size of your data set, you can have like more or less epochs. Sequence length is also good because it's a trade-off with the batch size, because the longer sequence length you have, so the bigger the context window, the more VRM you're going to use. But you don't need to use a sequence length that's as big as the pre-trained model. Then you have the batch size. You want to maximize it to maximize the utilization of your GPUs. And then you have the LoRa with the rank. This is like quite easy to fine-tune, so I don't want to go into the details here. Let's talk about model merging now. So model merging is the idea that you can take the weights of different fine-tuned models and you can combine them together. So you just can leverage what the open source community has produced on the Hugging Face hub, for example. It doesn't require any GPU, so it's super efficient, and it provides excellent results. So the OpenLLM leaderboard was updated this morning, so we have a version 2 now, but this is the version 1. I haven't had time to update it, but you can see that for 7B parameter models, The entire top 8 or top 10 is just merged models. So it really shows that this approach is extremely effective at producing high quality models, and you can find similar results on like really a lot of different data sets. You see that every node is actually a model, and we actually merge different merges together until it becomes like a giant family tree. This one is actually quite small, like it can get a lot crazier than that, but it didn't fit on one slide, so I chose this one instead. About the merge techniques themselves, I want to mention like a few of them. The first one is called SLURP. It stands for spherical linear interpolation. So the idea is really to apply spherical, but linear interpolation with the weights of different models. You can only merge two models at the same time with this technique, but you can really tweak it with different interpolation factors for different layers. Here's a model that I've made in your Beagle 14.7b, which was a really efficient way of leveraging the different models that were created by the open source community. And then you have there. So in there, you want to reduce the redundancy of the model parameters. To do that, you're going to use pruning. You're going to select the most significant parameters in your model weights, and you're going to rescale the weights of these source models. The advantage that it has is that you can merge different models, not just two, but even more together. And I would advise, I would recommend this technique, and not with just two models, not with three, but like with 7 or 8 models. It works really, really well. So I strongly recommend that. Then you have a very funny technique called pass-through. And in pass-through, you can concatenate layers from different LLMs. It can also be the same one. We call it self-merge. And so here you have an example that I've made recently. It's called Meta Llama 3 120b instruct, because I took Llama 370b instruct and I just repeated 10 layers 6 times. So you could say like this shouldn't work at all. Like, come on, you haven't even trained the model. This is ridiculous. But actually, yeah, this is ridiculous. People loved it on Twitter and Reddit and online in general. So it shows that there's a lot of things that we can still discover with these merge techniques, with these models. They do not, they can be counterintuitive sometimes, and you can see that this model in particular was particularly good at creative writing. It was also quite unhinged in general, but really good at creative writing, and now it's being used by a lot of people, even though it's super big.
But no kind of fine-tuning at all?
No fine-tuning, nothing. And then I want to mention the last technique, which is called mixture of experts. So in traditional mixture of experts, you are going to pre-train a model with a router. You can see on the bottom here, and different feed-forward network layers. And you pre-train it from scratch. But you can do something quite smart with merging, where you extract the feed-forward network layers from different fine-tuned models, and you combine them together like this. So we call this a Franken MOE. You add a router, you combine the FFN layers from different models, and this is how you create like your kind of mixture of experts. It's actually pretty cool. It works pretty well in practice. You can see on the left a merge kit config for the Beyond model. So for this model, I selected 4 different fine-tuned models, one as a chat model, one as a code model, one as a role-play model, and one as a math model. You can see that I'm using positive prompts here. So actually, it's a way to initialize the router, because if you go back to the previous slide, we can see that the router is supposed to select for each token and each layer where, like, which feed-forward network layer is going to be used. We use 2 in general. And so how do we initialize it if we do not fine-tune it? Once again, we don't want to fine-tune it. We can, but we don't necessarily want to. In this case, we're just going to use these positive prompts, calculate the embeddings, and use these embeddings to initialize the routers, and that works really, really well. So those are 2 models that I've used. For Fixtural, I had to modify it to make it compatible with Phi2, and that outperformed the base model on a lot of tasks. So it's really a good technique to use in general. But I would say that if you compare it to merging, as we saw with Slurp and with Dare, I would say that if you want to increase the performance, it's better to use Slurp and Dare instead of Mixture of Experts, because this is a bit more experimental. This will not bring you the same level of performance. And here you can see the results of the Beyonder model. You can see that the other models I'm comparing to are the source models that I've used in this merge. So it's quite remarkable to see that it's actually performing better than the source models on a lot of different benchmarks. So yeah, that's it for me. Thank you for your attention. If you are interested in knowing more, if you want notebooks to run some code, I created the large language model course. All these notebooks are available on GitHub, LLM course. And yeah, thank you. Yes, what do you want to know about Neural Daredevil 8B?
Well, I mean, I'm here, Jason, your blog post about how you made the Neural Daredevil and then you did the ablation, correct?
Yeah.
So that's also very VRAM-like, like it's all RAM-based, basically.
Yeah.
So like that's another technique that you could theoretically use, and you have a blog post on it.
Yes.
Right? Just wanted to throw that out there for you, just because I've used the model, it's amazing.
Thank you.
And it's like, and great post, thanks for the,
Thank you. Yeah, indeed, like you can use arbitration on top of all these other techniques. Didn't have time to really mention it here on the slides, but it's also like really cool to see all the mechanistic interpretability techniques that are now like, yeah, it's really amazing. Thank you.
Cool, we gotta move on.
Yeah.
Well, thank you everyone for joining the Open Models track. I know I learned a lot today, and excited for the rest of the expo and the rest of the conference here. So thanks for joining.